Hello, hi everyone, how are you? Today we are going to do a very beautiful question called delete a node in binary search tree. So it looks simple, but there are some edge cases in which it gets problematic. So let's just see. The question is pretty simple. Uh, you are given a particular k value. Let's just say k equal to 30 and you have to delete this node out of BST. So this looks highly similar to insertion, but there are some edge cases. So I'll explain you all the edge cases one by one. So let's first discuss on trying to delete k equal to 5. If I want to delete k equal to 5, it means this node. So what I have to do? I have to do its parent dot left, since 5 is left child, equal to null, right? I'll first go to reach to this 5. How will I reach? I am at 35. I know it's a BST, so left nodes are smaller, left subtree is smaller, right subtree is larger. Since 5 is smaller, it will be 100% on the left side. Then I reach 20. Again, I'm looking for 5, which is smaller, so it will be on the left side. I reach 10. I'm looking for 5, which is smaller, so 100% it will be on the left side. So I have to delete k equal to 5. Correct? So first thing is searching for the element. So for searching, I have already written down the boilerplate code. Now, first I have to delete this k value. I'm given the root node. I'm simply saying if root data, if I am 15 and you are looking to delete 10, I have to do the deletion from the left hand side. So I'm saying, hey tree, hey binary search tree, hey my left subtree, I'm making call to the left, delete 10, or maybe let's put it this way. Let's just say I am 15 and you want to do deletion of 10. So root dot data is greater than 10, 100%. So the data is on the left hand side. So I'm saying, hey left subtree, delete 10 out of yourself wherever it is, and then after deletion, whatever is the root of BST, just return me that. I'll make it my left child. Okay, this is how I'm doing the call. This is what my faith is out of recursion. Now this is the other case. The other case is when root dot data is smaller. So I am 15 and we are looking to delete 25. So then I am saying, I'm making a call to the right side because the data will be on the right side. Hey right subtree, delete 25 out of yourself and return me the root of final right subtree. I will make it my right child. And this else case is once we reach the data. So let's just see it happening. So let's just try to delete 5. So simple, I am saying I am at 25, I am at 35 currently. 35 will say, 35 knows 5 is smaller, so it will be on the left side. So 35 will say, hey left subtree, just delete 5 out of yourself, return me the final root of the tree, I'll make it my left child. This is what 35 is saying. That's what this call is. Correct? I will make it my left child. Root will catch it. After the deletion, whatever left subtree will return as its left child. Now I reach to 20. 20 looks like, oh, 5, we want to delete 5. I am not 5. So hey left subtree, delete 5 out of yourself. Return me the root of final tree. I will make it my right child. Now we come to 10. Again we want to delete 5. So 10 will say, hey left subtree, delete 5 out of yourself. Return me the root of final tree. I will make it my left child. Now I reached 5. I want to delete 5. What can I do to delete 5? Simple. I will return null. Because if I return null, what is actually happening? What was the call 10 made? 10 made that hey left subtree, delete the element 5 and return me the root of the final tree. I'll make it my left child. So if 5 returns null, 10 will catch null in the left child and 5 will automatically get deleted. Make sense? Now what 10 will do? What was the call 20 made to 10? So 20 simply said, hey left subtree, delete 5 out of yourself, return me the root of the final tree. So the root is still same 10, only instead of 5 null is attached here, and so on and so forth. So this is how 5 will get deleted. So let's quickly complete the code. So simple, this is the case, this was just making the calls for left and right side. This else part is when I reach the data. So I'm deleting a guy, I'm deleting a leaf guy. Okay, there are 3 cases. First we are discussing the case when we are deleting a leaf guy. For example, 5 or 30. I'll show you for 30 also. When 0 child, when 0 children. Basically, I'm talking about a leaf guy. So how will you define it? Simple. If root dot left double equals to null and root dot right double equals to null, double equals to null, In this case, I'm a leaf guy. I have to simply return null. Okay, easy peasy. Now let's just see the same for k equal to 30. So I am at 35. 35 will say, okay, you want to delete 30. Hey, left subtree, delete 30 out of yourself and return me the root of final tree. I will make it my left child. Now you reach to 20. 20 sees, okay, 35, you want to delete 30, which is greater than me. So 20 will say, hey, right subtree, delete 30 out of yourself, return me the root of that tree. I'll make it my right child. Now you reach to 30. Simply what you are doing here, you simply return null. Who was waiting for it? What was the call of 20? 20 said, hey, right subtree, delete 30 out of yourself, return me the root of the tree. I'll make it my right child. Since 30 returned null, null got attached to it. 20 returned himself only. So 35's left is 20, and here I have a null. That is how 5 and 30 will get deleted. Hope it makes sense. So these two are done. This will work. Okay. Now coming to case 2. What is actually case 2? Case 2 is when you want to delete something which has one child. For example, 10 and 41. So let's just say you want to delete 10. 10 is having one child. Now here you cannot return null. If you return null when you are at 10, in 20 is left, you will get null. But where will the 5 go? Or let's just say you want to delete k equal to 41. If you delete this guy directly, what will happen to rest of the tree? So since it has only one child, what will we do? If I delete 41, 51 will take its place. If I delete 10, this 5 will take its place. So it's pretty simple, right? If the node that we are deleting has only one child, the one child will replace that guy. Okay, so again, how the calls will be made? We want to delete, let's just say k equal to 10. So how k equal to 10 will happen? 35 will say, hey, left subtree, since 10 is smaller than it, 10 is 100% on the left side, delete 10 from yourself, return me the root of that after deletion. I will make it my left child. Now you reach to 20. 20 says, okay, 10, you are 10, so you are smaller than me. Hey, left subtree, delete 10 out of yourself, return me the root of that final tree. I will make it my left child. Now I reach to 10. 10 says, okay, I am the guy that has to be deleted, but I have only one child. So what to do? 10 here at this node at 10, you will return your single child. So what will happen? Instead of this 10, this 5 will be returned and 20 will catch it in its left child. 35 will catch 20. If not clear, maybe you'll get it in this example. So let's just try to delete 41. Although 41 is pretty simple, but let it be. So 35 will say, we want to delete 41, which is larger than me. So hey, right subtree, delete 41 out of yourself, return me the root of the final tree. I'll make it my right child. Now you reach to 41. You cannot delete 41 directly, because then what will happen? If you simply return null, 35.right will become null. Then what will happen to this part? But since 41 has only one child, what 41 will say, instead of returning null, let's return my only child. So 41 will return its only child and 35 will catch it. So 35's right will become 51. Okay, that's how the deletion will happen. So if you want to see, maybe this is how it will look like. If I want to present it, maybe I can copy paste. Copy. Then let's add a new page. So this is how the deletion of 41 will happen. When we reach 41, 41 will return its only child. So this thing will get removed and this whole part will get attached here. So you can see it's still a BST. Okay, the BST property has to be maintained. I mean, you cannot change that if you're deleting in a BST. So this is how the tree will look like. Again, 35's greater is 51, left side all smaller, right side all greater. So this case is also easy when you have one child. So let's just quickly write it up. So we already checked if the node has no child. Now how will we check if it has a single child? So simple, I will say if root dot left is equal to null, I'm 100% sure if I'm reaching this if that both the things are not null. If both the things are not null and left side is null, then 100% right child is the only child that the node have. So simple, I'll return root dot right. Maybe we can write all of them in else if root dot right double equals to null, simply return root dot left. I'm 100% sure that both the children are not null and left child is not null, so 100% right child is null. So in that case, you return the left child. Now comes the most tricky case, the final case, which is, you can guess, when a node has two children. Not this one, 51. When you want to delete 51. So let's just see how the deletion of 51 will happen. So first of all, you have to analyze it from the diagram. What will happen with the deletion? So if you want to delete 51, okay, we want to delete 51, what should come at its place? If 51 is not here, what do we want to be in the place of 51? If you move this right tree, where will the left tree go? And if you move this left tree, I mean, you want to delete 51. If instead of this 51, you put this right tree here, where will this left tree go? If instead of this 51, you move this left tree, where will the right tree go? So there are many ways to that, but there is one very simple way that I want to discuss. So let's just say I want to delete 51. Okay, I will not do the direct deletion. Instead, what we will discuss, what we can replace 51 with. I mean, I want some value here to which everything on the left is smaller and everything on the right is greater. So what can be here? Can I put 48 here? Let's just say I remove this 48 and I make it 48. So is this still a BST? Is everything on the left smaller? Everything on the right greater? So everything on the left smaller. Oh, instead of 48, maybe I'll give you another example. Instead of 48, let's pick 45 first. So if I remove this 45 and put it here, is everything on the left smaller? Obviously no. Everything on the right greater? Yes, this is there. But everything on the left is not smaller. So 45 cannot be here. Now maybe you can try to guess what can I take from the left side, delete it and put it here. So I think you might have guessed 48. So you can delete this 48 and put 48 here. Why? Because 48 is largest child of the left side. So 100%, since it's largest, everything on the left is smaller. If I'm picking the largest child, largest node of left subtree of this 51's left subtree, 100% everything else will be smaller on the left side. And since it was on the left, everything on the right side would be larger. So 48 is my guy. Apart from 48, what else you can think of? So we can pick minimum from the right side also. So I could have picked 55 also, because if I pick 55, again, what will happen? Everything on the left will be smaller because this is coming out of right side. And since I'm picking smallest of right side, everything else on the right would be larger. So I can replace my 51 with anything like 48 and 55. So it's totally your call. You want to choose maximum of left side or minimum of right side. Okay, let's write some code. So simple. First of all, let's get maximum from the left side. Int v is equal to max function. You can write max of root dot left. Then what? You make your root dot data is equal to v. So what I have done till now, I'm saying I picked the maximum of left hand side. So I picked 48. I replaced it with 48. This is what I have done till now. Okay, I wanted to delete 51. Now what I can do, but still there are two 48s, right? And there can't be two 48s. So what to do? In the left side, I have to delete 48. And haven't we written it recursively? So what will I say? What you have to understand, I'm still at this place. I'm saying I'm calling delete function on my left side. And what do I have to delete this time? V value, the maximum value that I replaced my current node with. And where do I have to catch it? In current roots left. And in the end, what do we have to do? We have to return root. Make sense? So this is what we have done. Hope it makes sense to all of you. Simply what you have done, you picked the the maximum out of left side, replaced yourself with that, and called delete function on this part. So only 148 can be found now, which will come along this side. And since this will happen on recursively, eventually 48 will get deleted, right? So hope it makes sense. Now coming to time complexity, you can remove this empty page. So first you are searching for the element. Let's discuss one by one for all the three cases. When there were 0 children, 100% I am just reaching till the leaf, and that is order of h. Every time I'm skipping one height, right? When I'm deleting 0 children guy, I'm reaching till the height. I mean, worst I can go till the height of the tree, because every time I search for an element, I either go to left side or right side, so I skip a level. So in this case, it is coming out to be order of h. Now, when somebody has one child, even when somebody has one child, it can happen that one child guy is here, so it's height -1. Worst we can go is height -1, because here we don't do anything. We just reach that element, and after reaching we return whatever is on whichever child the single guy has, left child or right child. Okay, so almost order of h. Now you might have doubt in the third case. So in the third case, first thing that you do is you reach to the element. Okay, so the element can be up to height -2 level or height -1 level. So order of h you will take to reach that element. Then to calculate max, you will take another order of h one time. So order of h plus order of h, because this will get called only one time, this max. Then you are calling delete on that part. So basically what you have to understand, first you reach till 51. Okay, then you got the maximum out of here. Okay, now this although will not be order of h, calculating maximum of a BST is order of h operation, right? So order of h on this side. So for searching the element, you can take maximum order of h, and let's just say you some 3 units of height you took here to reach the element. Once you're deleting the element, again the worst you can go is up to h -3. Simple. Let's understand it this way. Let's just say the node I had to delete, which had 2 children, this is where I found it. Okay, at some x height. Now from the remaining this much part, from this remaining y height, first I found the maximum. Okay, so x plus y, then what? Then I'm calling delete in this part, which will again take maximum order of y. So x plus y almost order of h, because x plus y is h. X plus y is nothing but height of the tree, and this y is what? Something lesser than h. So overall this is order of h. Hope it makes sense to all of you. So time we will take is order of h. Thank you so much. Hope you enjoyed. See you in the next video.